Good morning, good afternoon, and good evening, everyone. Welcome to another RTDS Technologies webinar. This webinar is part of our User Spotlight Series 2.0, which is a series of webinars where we're featuring our users and the applications and projects that they're taking on with the RTDS simulator. So today we will have two exciting presentations. They're on the shorter end in the 15 to 20 minute range, and then after both presentations have concluded, we'll have the opportunity for a live Q&A session. My name is Katie Sidwall. I'm the Technical Marketing Lead at RTDS Technologies, and I'm happy to be your host and moderator today. If you haven't used our webinar platform before, take a moment to familiarize yourself with it. The Q&A widget close to the top left-hand corner is the most important. This is the place you want to submit your questions via text throughout the webinar. So as soon as you come up with a question, please go ahead and submit it, and our presenters will be available to answer your questions by text throughout the webinar, and then we'll have a few discussions about them at the end as well. If you're interested in downloading the slides for this webinar, you can do that now. They're available in the bottom left-hand corner in the Handouts or Additional Materials section. And we will also be distributing them to all attendees after the webinar. So don't worry about getting the recording or the slides or the Q&A document. All of that will be sent to you automatically after the webinar is concluded and we've put together the Q&A document. You can also always access these webinars via YouTube as well. And lastly, you'll see a chat widget on the right-hand side. Please feel free to use that to say hello. Let us know where you're joining us from. It's great to see familiar and new names here. Hopefully we'll be back to seeing faces soon enough. A couple of quick notes before we get to today's program. If you're not familiar with RTDS Technologies, we are headquartered in Winnipeg, Canada, and we pioneered real-time power system simulation in the 1980s with our product, the RTDS Simulator. And our simulator is the industry standard when it comes to closed-loop testing, or hardware-in-the-loop testing, of power system protection and control equipment, and it's typically used by electric utilities, manufacturers, research and educational institutions, and power system consultants around the world. So you can learn more at rtds.com, and I highly recommend that you check out our YouTube channel. We have a large library of videos there, from past webinars to shorter educational videos. There's something for everyone, so take a look. I also have some exciting news. We have some in-person training courses coming up. We used to host these regularly pre-pandemic, and we're very excited to be getting back to our program. So in September, we will be hosting an introductory RTDS simulator training course. That's a great course if you have little to no experience with the simulator and you want to get familiar with both the software and the hardware aspects of the tool with hands-on help from RTDS experts. So that's September 12th to 16th. And then we have an advanced course the week after that. It's Advanced Applications, Renewable Energy, and Microgrids. So that's for people who are already familiar with the simulator's basic operation and they want to enhance their knowledge. We'll be going into DER simulation and options for converter simulation as well. So that one is September 19th to 23rd, and those are both located at the RTDS Technologies headquarters in Winnipeg, Canada. You can find out more and register for the courses by visiting our website, and those links will be included in that Handouts or Additional Materials widget as well. All right, that's enough housekeeping. I'm moving on to introduce our first presenter. Presenting CHIL Microgrid TESTBED, we have Guilherme Justino from PTI, or Parque Tecnológico Itaipu, the Itaipu Technologic Park. Guilherme received his BSc degree in electrical engineering from the State University of West Parana, Brazil, in 2011. Currently, he works as an electrical engineer in Itaipu Technologic Park. He's been working on power system analysis and microgrids and renewable energy applications in real-time simulation. Please welcome Guilherme Justino.
Thanks, Katie, for the introduction, and thanks RTDS for inviting me to participate in this session of User Spotlight Series. My name is Guilherme Justino, and today I would like to share a little of our experience in a project we carried out where the objective was to implement a real microgrid in a rural distribution system in Brazil. My presentation will proceed as follows. First, I will give a brief presentation about the project, then I will show the microgrid composition, then I will talk about the microgrid control logic, then I will present the microgrid testbed developed for this project, and then I will show the results obtained in laboratory in the field. The project's main objective was to demonstrate the technical feasibility of microgrid through the implementation of a real microgrid. The participating companies were Itaipu Power Plant, the project founder, PTI, responsible for the control, protection, and monitoring systems, CI Biogas, responsible for the biogas production system and biogas generator, and Copel, operator of the distribution system in the region. The location for implementing the microgrid chosen was the region near Colombari Farm. Due to a series of advantages listed here. The farm has 5,000 pigs and there are 150 head of cattle, which allows an average daily production of 1,000 cubic meters of biogas. In addition, the farm already has a biogas generator that attends to the farm loads and exports the excess of energy to the distribution grid. Another relevant feature is the location of the farm. As it is connected to a rural feeder, power outages are more frequent than usual. In addition, for Copel's point of view, it is safer to carry out experiments in the region with a fewer consumers than a well-populated area. This figure represents a microgrid built during the project. It has about 6 kilometers of network and is limited by these two reclosers. Besides the Colombari farm, 3 other consumers are part of the microgrid, where one of them is supplied by a 3-phase transformer and the other 2 are supplied by a single-phase transformer. Also part of the microgrid is the 105 kVA biogas generator, the microgrid control center, and the protection panel, which acts on the circuit breaker, and the generator control panel, which works on the MCB and GCB circuit breaker. The MCC monitors all water microgrid controls equipment, and it also has responsible for running the algorithm responsible for allowing or not the microgrid island operation. Here are listed all conditions that must be satisfied for the MCC to allow the island operation of the microgrid. Starting with the recloser, it must have no voltage reading from the substation side. In other words, there is a lack of voltage in the distribution grid. There cannot be a current trip signaling. As the distribution system is radial, a current trip means a fault at some point in front of the recloser, which may be inside the microgrid. This condition prevents the formation of the microgrid due to a lack of voltage caused by a fault inside of the microgrid. The trip loop scheme must be signaled. The loop scheme function is an undervoltage function for the bus side of recloser. After predetermined time, it will act and prevent the recloser from closing even the voltage returns to a normal values. The third condition for the recloser is that it must be open. The condition associated with the PSP is that the circuit breaker must be open and the relay cannot detect voltage on the grid or the load side. When all these conditions are satisfied, the MCC will allow microgrid island operation. The GCP will receive a signal from MCC allowing to close the MCB, and the PSP also will receive a signal from MCC changing its set group protection, which will allow closing the CB. Here are the conditions for the MCC interrupt island operation, going back to the operating in standard way, in parallel with the distribution grid. The first condition is the reestablishment of the distribution system. Once the substation side recloser detects voltage in the bus side, the MCC no longer allows island operation and starts the procedure of reconnecting the generator in parallel with the distribution grid. The other conditions are signaling any trip on the PSP or GCP. In this case, the MCC assumes that the microgrid is not longer secure to operate, and if it's possible, the columbary farm operates in isolation. If any of these conditions occur, the MCC reverts to default operating mode. One of the project stages was to create the microgrid that would be implemented in a laboratory environment. In this way, it would be possible to evaluate all operation aspects in the safe and controlled environment. The main equipment that compose the test bed is, marked with 1, the RTDS Nova Core, where the whole power grid components of the microgrid were implemented, as a distribution system, transformer, generator, and circuit breakers. In 2 are the automatic reclosers controllers from Eaton manufacturer. Coppel widely uses this model in their feeders. In 3 is the MCC, which is a controller from Schweitzer manufacturer. This model was chosen for being modular and versatile, being able to cover any unforeseen during the process. 4 is the GCP from the manufacturer CISIS. This same model is already used in Columbary Farm. 5 is the protection relay that makes the interface between the distribution system and the consumer, also the same model already used in Columbary Farm. In 6, it's the emulator of the distribution system operator, who remotely access the controllers. And 7, it's the GPS, used to leave all equipment with the same timestamp. In addition, at the back of the rack are the radio transmitters and media converters, which can be used for communication between the recloser control and the MCC. After assembling and configuring all the equipment, the laboratory test stage began. The ideal test condition would be connect all equipment to the RTDS simultaneously. However, at the time of these tests, our laboratory had not yet updated to the Nova Core RTDS, and unfortunately, we did not have enough hardware to continue in this way. Therefore, the tests were done in parts, connecting some of the system and emulating the rest. The objective of the test was to verify the behavior of the microgrid's communication, control, and protection systems. For this, test routines were prepared with the different types of events, such as lack of voltage and failures along the distribution system. After installing the equipment in the field, tests were also carried out to release the microgrid operation. But only one time of test was carried out, lack of voltage in the microgrid area. The evaluation was performed in real time, with people positioned in both reclosers and the MCC. On the left is the picture of a sequential of event report from MCC after completing the tests. And at the right is the diagram representing the current state of the network. At that moment, the network is in normal operation mode, with the generation operating in parallel with the system. At that moment, the test starts, and the Coppel team cuts the energy supply for the microgrid area. In this sequence of events, the two recloser controllers stop detecting the voltage at the bus side. In addition, the Columbary farm starts operating isolated without connecting to the distribution grid. After 1 minute without power, the reclosers signalize trip loop scheme, opening the circuit breakers and isolate the microgrid area. At that moment, all conditions for microgrid island operation are satisfied, so the MCC indicates this condition to the PSS and GCP. After around 1 hour of island operation, the Coppel team returned the supply energy to the microgrid area. Thus, the automatic recloser 1, which is in direction of the substation, detects the voltage at the bus side. And how this is one of the conditions for interrupting the island operation, the Columbary farm returns to operate isolated from the distribution system grid. About 20 seconds after the interruption of the island operation, Coppel's operators team cleared the loop scheme trip signal and closed the automatic recloser, reestablishing the normal operation of the distribution system. 5 tests were carried out to verify the beginning and the end of the microgrid operation logic. During the tests, the microgrid operated for approximately 7 hours, providing around 250 kilowatts-hour for external consumer. At the end of the tests, Coppel allowed the microgrid to operate. After that, the project had another 2 months of assisted operation. In this period, the microgrid was formed 3 times, operating for 35 hours and supplying approximately 400 kilowatts-hour to external consumer. Implementing this microgrid was a challenging task. At the beginning, there were many doubts about how to reach the objective of the project. However, having the possibility to carry out the tests in a laboratory with the same equipments would be in the field allowed our team to learn a lot during the development and without worrying about the possible errors. Furthermore, as there is still no regulation for island microgrids in Brazil, performing tests with this testbed gave Coppel security, allowing the projects to be carried out in the part of its grid. I finish here my presentation and thank you all for the attention. I also thanks to the RTDS for the initiative. I leave here my contacts. Please feel free to contact me to discuss the topics of this presentation. Thank you all.
Thank you so much, Guilherme, for your presentation, and thanks to the audience for your attention and for your questions. Moving on to our second presentation, and then we'll get to the live Q&A. Next up, we have Cyber Power Testbed Development, presented by Mohammed Mustafa Hussein from West Virginia University. Mohammed Mustafa Hussein is a research assistant and doctoral student working with the Smart Grid Resiliency and Analytics Lab, SG-REAL, at the West Virginia University. He's working on cybersecurity and cyber resiliency of the smart grid along with the development of a real-time multi-vendor hardware-in-the-loop testbed for real-time data generation, application validation, and cybersecurity use cases. He received his master's degree in computer science from Washington State University in 2021. He worked on cybersecurity and resiliency of synchrophaser systems using multiple testbeds developed during his master's work. Please welcome Mohammed Mustafa Hussein, presenting on Cyber Power Testbed Development.
Hello everyone, this is Mohammed Mustafa Hussein. I'm a PhD student from Smart Grid Resilience and Analytics Lab, SGDL, in West Virginia University. And today we will be talking about the research work that we are doing, which is focused on cyber power testbed development and cybersecurity analytics for smart grid resiliency. So I will start my presentation by thanking RTDS to give us the opportunity to present our work here through User Spotlight Series 2.0. So let's start the presentation. So power outage caused by hackers. The highly dangerous Triton hackers have probed the US grid. Major power outages in India possibly caused by hackers. Hackers trigger yet another power outage in Ukraine. Ukraine power grid lucky to withstand Russian cyber attack. So these all newses points to one direction where we can see that power system, the smart grid, equipped with a lot more cyber components than ever before as a form of hardware and software, is one of the prime target for hackers to attack and bring it down. So what can we do about it? So there are two ways and two portion that we can work on. First of all, tools. We can develop tools for cyber resiliency, such as algorithms and tools for cyber anomaly detection, classification, localization, root cause analytics, and resilience analysis. Then, second thing that we can do, we can develop a real-time cyber power testbed, which can stream real-time cyber physical data, which is equipped with cyber components similar to the power system in real power systems, and which is capable to validate the tools that we are developing in the first phase. So this is the summary of my presentation. So I will start from talking about that why the cyberpower testbed is needed, and then I will talk about the cyberpower testbed that is being developed in SGDL lab, the tools that we have developed on top of cyberpower testbed to validate and integrate that in the control center, and overall how we are using the tools and cyberpower testbed as a whole in our lab. So first of all, why cyberpower testbed is needed. So let's start from this point, that why real-time testbed with co-simulation is required. So as I discussed earlier, that electric grid is becoming increasingly complex with new technologies and services such as distributed energy resources, Internet of Things devices, new communication network technologies. And due to those things, we are prone to more cyber attacks, which we can see from the Stuxnet malware and Ukraine attack. And this deploying new technologies needs extensive testing and validation before the actual deployment. And the important thing is that this is not realistic to test all these new technologies and these new algorithms in real power system before the deployment, which would have definitely helped us in deciding that whether these are really secured from the cybersecurity point of view. So for that reason, the real-time cyber physical testbeds provides a confidence in solution so that we can validate these tools, technologies, and algorithm in the testbed, and then if these are validated in this real-time cyber physical testbed, we can deploy that in the real system. So let's talk about some of the challenges that we have encountered, and in general these are the real challenges that anyone has to encounter while developing real-time cyber physical testbed. So the challenges can be divided into four major categories. First of all is the synchronization between dynamic power system and discrete cyber network systems. And for this, we do have different solutions, and the solution differs according to the approach of the type of the testbed we need to develop. In our case, we have developed hardware in the loop testbed. So using NS3 and ACL software-defined network switches to exchange data in real time to solve this synchronization problem. Then comes the interfacing with multi-vendor hardware and software components. When we are dealing with real-time multi-vendor cyberpower testbed, we have to deal with different components. Then we have to study the protocols and standards and come up with a common supporting standards and protocol which supported by all, and also suffices the real-time data streaming requirements. Then developing logging and data storage systems, which involves both power and cyber data. And for this, we do have many solutions, and it also differs from the type of the testbed that we are developing. In our case, we have used a combination of MySQL and cloud database along with Splunk to create a real-time logging system. Then comes the creating real-time cyberpower scenarios to validate this monitoring and control tools that we are developing. For this, we need to create different cyber attack and power system events, and those events, to create those events, the testbed needs to be more realistic and have the different discrete components which suppose those events. So in general, these are the challenges and possible solutions that we can take to approach towards developing a real-time cyber physical testbed. And now let's talk about the cyberpower testbed that we have and we are developing in our lab. So first of all, this is an overall picture of the cyberpower testbed. We are using RTDS real-time digital simulator, which is where we are simulating transmission system and distribution system separately, and we have created network simulators, communication network using network simulators and the different network simulators and emulators, which is connecting all the sensors and controllers, which is taking the streaming data from RTDS and giving those data to control center applications via these communication networks. So this is a more detailed view of the cyberpower testbed, where we can see the energy management system and distribution management system we have on top of this cyberpower's physical system and communication network, and the tools that we have developed in our lab, CPTRAM and CPSAM, which provides the resiliency of power systems when an event occurs. Now let's start from the power system modeling portion. So we have developed a dynamic model to represent the field systems. This is an electromagnetic model developed in RTDS. And we also have developed a realistic static model in control room using Power Simulator. Power Simulator is a realistic platform for power system operation and control, which is developed by INSYS and Power Data. It's also a dispatch training simulator where user can interact with this Power Simulator to get the training for as a control room operator using different cyberpower scenarios. And for our power system modeling, we are developing a CASCADIA test system. CASCADIA test system is a power system model which is in the power simulator, which is modeled in the power simulator, where user can create different power system events and train themselves about how to react how to react and control those events in real time through the power system model. So this is a Cascadia test model that we are developing in RTDS as a part of our presentation, as a part of our testbed development. So from the left hand side, we can see the power system web user interface, where a user can interact with the Cascadia power systems. And in the right hand side, we can see the system schematic of Cascadia power system model, which we are developing in the RTDS. So let's talk about some Cascadia power system highlights, where we have a total number of substations, 54, and then we have 21 generating substations, mainly hydro, thermal, and natural gas. The largest generator is at Chehalis with 1200 megawatt capacity, and the Cascadia deals with power transfer through 115 kilovolt, 230 kilovolt, and 5 to 25 kilovolt lines. So, and on top of that, this is a test representing the Washington state area, and it's covering the whole transmission systems of the Washington state. So in RTDS, we have modeled the western region budget of Cascadia, where we have modeled the transmission. Each substation is modeled as a bus for simplicity, the transmission substations, and the transmission lines are essentially modeled as R and L components. Sources are simple voltage sources, and we have modeled the load as dynamic load operated as static loads, and the real power converges similar to INSYS Cascadia after 6 iterations. And this is a voltage and power waveforms from a substation in the budget area, which is modeled in the RTDS. So this is basically a power system model that we are developing the RTDS for our test case. Now let's talk about the substation modeling and wide area network modeling that we have here. So this is a picture of the substation or network in SGDL lab, where we have RTDS for power system modeling. We have ACL Schweitzer Engineering Laboratories, ACL devices in our lab to automate and model the substation networks in real time. And we have workstation HMI to monitor and control substation remotely. So we can see the different components here. We have where we have RTDS, we have real-time automation and controller working as a local PDC and local historian. We have software-defined networking switches connecting substation network. We have substation workstation and local HMI. We have ACL relays and PMUs connecting to the RTDS, and we have ACL GPS for time synchronization. which is taking the time from satellite and synchronizing the RTDS initial device with a similar protocol. And this is a more schematic view of the substation that we have in our lab, from where we can see that each and every device is connected to each other via the software-defined networking. And I will talk about the benefits of the software-defined networking in my next slide. So this is the schematic HMI view for the software-defined networking, where we can see that every device is connected with each other through the SDN switches, and the network flows are created accordingly. The benefit of using software-defined network is that it provides greater reliability by automation. It provides more efficient network management, and it provides more and improved security in the substation level. So till now we have talked about the power system modeling and the substation automation, and this is the schematic diagram of the end-to-end data connectivity from substation to control center using NS3, where we have substation cyber network modeling. We have modeled the communication network in network simulator, where we have taken a transmission bus as a communication node and connected the communication nodes following the physical model, as a physical model mapping 1-to-1, and then this NS3 is connected to OpenPDC, which is in the control center. And more importantly, we are storing and logging the data from substation, NS3, and control center in our logging and archiving databases. So now let's talk about the control center modeling and cyber log monitoring system that we have. So this is the picture of our control center that we have in the SGDL. This is divided into two parts, like one is power system operation center and the second one is network operation center. And the dashboard from the screenshots shows in the previous slide and in the upcoming slides are shown in this control center. So this is one portion. This is the SGDL cyber log monitoring system that we have. The cyber log monitoring system, this is one example of analyzing the missing synchrophased data using our dashboard and data logging management systems, where operator can investigate the synchrophaser data issues and data qualities in real time using this monitoring system. And here we have substation traffic analysis, which is also another supplementary cyber log monitoring system that we have in our lab, which is taking the network traffic in real time and segregating the network traffic according to different deciding parameters that we have. Now let's talk about the integration with resilience analysis tools. The tools we have developed in our lab and integrated with our TESTBED, which is helping and which is developed with the goal of assisting operators in real time about understanding the state of the power system. So first tool that I'll be talking about is called CPTRAM. CPTRAM is a cyber physical transmission resilience analysis metric tool, which can take different physical factors and cyber factors and run different algorithms within itself to show the resiliency in real time when an event happens in the power system, which can help operators to understand the state of the power system, the resiliency state of the power system. So here there is a two dashboard that we can see. One is for physical event and one is for cyber event. And this tool incorporates different physical and cyber factors, such as for the physical factors, it incorporates generator availability, number of physical operations, matrix redundancy, power system measurements. For cyber factor, it incorporates the cyber path length, the network redundancy, network configurations, the exploitability through cyber vulnerability scoring system, and cyber vulnerability exposure databases, network flows. So after incorporating these different metrics, it provides a real-time resiliency score, a number which can help operators to quantify the resiliency in times of a cyber or physical event. And this is another tool. This is called CPSAM. CPSAM is a similar tool like CPTRAM, but the major difference is that it is used in the distribution system. It incorporates the cyber physical factors related to the different cyber physical factors, which is related to the distribution networks, and it calculates the resiliency in real time when an event in cyber or physical event happens um, in the distribution grid, and shows live physical and cyber maps and the points where the event is happening, and also shows the resiliency score from which operator can understand that some event is going on in the power system, and due to that the score is going down accordingly. So basically these tools are developed with the goal to help operators in to take decisions based on the power system state, and also to understand the real-time power system resiliency state. And in our case, we have integrated and validated these tools. We are doing that in the real-time cyber physical testbed that we are developing here, and um, we are also in the process of developing more tools which will help operators in more directions. So coming to the summary of our work, we have developed a real-time multi-layer cyberpower testbed where we have used real-time digital simulator as a dynamic power system simulator. We have used both software PMUs and RTUs, as well as ACL hardware relays and RTEC for substation level automation with software-defined networking. We have used network simulator to create wide area communication network on top of physical power systems. For logging and data storage system, we have used MySQL database, Node IDS, and Splunk logging system. We have developed different advanced tools to help operators with better decision making and situational awareness. And we are able to generate synthetic but realistic data for validation of algorithms and tools. And last of all, we are creating different cyber attack and power system events to understand the nature of interdependency within cyber power system. Lastly, we acknowledge the technical support from other students, postdocs, RTDS, ACL, and financial support from the US Department of Energy and National Science Foundation. So this is the end of my presentations, and I'll be really happy to answer any questions that you have in mind. Thank you.
Thank you so much, Mustafa, for that presentation. And thanks also to our presenters from PTI, Guilherme, and he's joined by his colleague, Paolo, here for the Q&A as well. And I hope everyone can hear me clearly and we don't have any technical difficulties today. Let's jump into some questions for our presenters. I'll start out with a question for Guilherme and Paolo from PTI. Could you expand on how the equipment in the microgrid testbed was physically connected to the RTDS? So maybe talk about some of the I/O that was used. I saw Modbus mentioned in one of the diagrams, so maybe you could talk a little bit about how communication protocols were used for interfacing in your project.
Hi, can you hear me?
Yes, it sounds clear.
So, okay, about the connections, we did the tests in parts. We At the time we didn't have the infrastructure from RTDS enough to connect all equipment at the same time. So in the first stage of the tests, we connected the automatic recloser controllers and the microgrid controller. We used the current and voltage amplifiers, about, if I remember, about 12 of each one to feed the voltage and current inputs for this equipment. And at this step, we would like to verify the behavior of the recloser control and verify verify also the connection between the controller and the microgrid controller. This connection of the communication were made by fiber optic, and the protocol used was Modbus. We send mainly the trip loop scheme signal from auto recloser control to the microgrid, because it is one of the conditions to for us to make the island operation. The second stage of the test was connect the microgrid controller and the PSP relay protection control on the RTDS, also using the voltage and current amplifiers to feed the inputs of the relay. At this stage, we would like to verify the performance of the protection settings and also the communication between the microgrid controller and the relay. We also connected the generator control, but only the communication part. In this stage, we also emulated the behavior of the automatic recloser controllers, because we don't have the enough infrastructure to put all this equipment on the RTDS. The communication between the microgrid controller and the relay protection was made by binary output and binary input. It's a digital communication, and between the relay was this communication is needed to change the setting group from 1 to 2, where the setting group 2 was for the settings of a microgrid island operation, and the setting 1 is do the parallel operation. So when the microgrid determines to operate in island mode, the setting group of the PSP relay have to be 2. And the communication between the microgrid controller and the generator control was also by a digital input and output. In this case, it was important to make this communication, because when the generator is working in parallel to the grid, the strategy of... Wait a minute, please. The strategy was, when it was in parallel to the grid, is he's working controlling the power and the power, active power and the reactive power inject to the grid. And when it is in the island operation, it has to be changed to the voltage and frequency control. So the microgrid controller also send a signal to the generator control to make this change. I believe I answer all the question, Katie.
Yes, definitely. Thank you. That's very clear. Okay, let's go to a question for Mustafa. Mustafa, I wonder if you can elaborate on how the RTDS and the network emulator were connected, which type of protocols were involved in that connection, and how you established the real-time interface. Okay, I think we might be having some technical difficulties on Mustafa's end. So instead, let's switch to another question for PTI, and we'll go back to Mustafa momentarily. Guilherme or Paulo, What are the load types supplied by the microgrid, and how did you model those loads in the RTDS?
Okay. The loads, the microgrid is located on a rural area, right? Then two types of load can be often encountered in this kind of situation. Small farms where there are no machinery, the loads found were typically residential, small loads with little or non-dynamic interference for the R simulation. However, in large farms, induction motors are commonly found performing different types of tasks. However, the largest um, at at this microgrid, the microgrid Columbari, the only one consumer that have this kind of component is the Columbari farm. He has a lot of this kind of component, the induction motors, but he also have the soft starter components to control the start of the motor. So the that condition of overcurrent at the starting the motors are not relevant to our simulation. So we decided to represent all of the loads by using passive elements like resistors and inductors, seeing the level of power that each element consumes.
Okay, thank you very much. Let's try again to speak to Mustafa. Mustafa, can you unmute yourself?
Hello, can you hear me?
Yes, we can hear you.
Okay, thank you. I refresh the
Excellent.
session again. Yeah.
Okay. So we have a question about how you connected the RTDS to the network simulator. Which protocols were used to establish that interface?
So, to connect RTDS with the external network simulators, we have used RTDS GTNet module, and we have a GTNet card supporting two module. And first of all, we have used a combination of different protocols. The one protocol that we are using currently is 37.118. It represents the standard for synchrophaser communication. So we have used that protocol to stream data from RTDS to the external through the external network to the control center. So for that we have used a combination of software PMU and hardware PMUs, mostly software PMUs, and then configure the software PMUs accordingly according to the standard of 37.118. Then what we have done, we have connected the ACL RTEC as a server client topology methodology with the RTDS to communicate the power system model through 37.118 and stream data accordingly. Then again, we have used another protocol called sample values to model the 61850 auto substation automation to stream the voltage and current measurements at 4800 frames per second rate to ACL relays so that we can have the necessary data for substation automation. And yeah, so we are using these modules interchangeably. Sometimes we use DNP3 also instead of SV. So it depends on the modeling that we are doing and the specific use case that we are performing.
Excellent, thank you. And if any of our listeners are interested, we do have a tutorial available on connecting NS3 to the RTDS via the GTNet card. In our tutorial, we use the socket protocol, so it's not involving synchrophaser data like in Mustafa's case. But if you're interested, definitely contact us for that. Okay, let's go to another question for Mustafa here. Mustafa, someone asked in the chat if you mind sharing one or two of the specific attacks you tested and what their objectives were on the power system.
Yeah, thank you. So we are continuously developing and performing different cyber attack scenarios in different approaches. So the cyber attack scenarios that we are performing can be divided into two broad categories. One is insider attack and one is outsider attack. For the insider attack, we are performing different versions and different ways of man in the middle attack with different approaches and specific attack goals. And for the outsider attack, we are trying to exploit particular CVEs, which is related to mostly the softwares and hardwares of the power system, and to gain the remote access of the automation system and disrupt the control and monitoring capabilities. So these are the two broad areas of cyber attack scenarios that we are continuously working to develop, and our goal is to see how the power system and cyber power interaction uh, changes our power system, uh, how the power system impact can be analysis through the attack scenarios or can be impacted through these attack scenarios. And our another goal is to develop different resiliency based tools which can capture all these changes that has been done due to the cyber and power events, and then can show some interactive outputs to the operators which can help them to identify different events that is happening in the power system. I hope I answered the question.
Yes, I think you did. Very clear. Thank you. Let's go back to Guilherme and Paulo from PTI. Could you talk a little bit about any studies that you conducted throughout the project and how they were conducted?
Okay, we performed three kinds of studies along the project: power flow, stability, and short circuit. Power flow studies were done to support the microgrid size. For this, a study of loads was carried out in the region of the Columbari farm, verifying the average consumption and the load type that each consumer has. After that, we collect the data about the loads were represented in RSCAD. A factor demand of 70% was applied for the heavy load scenario. And with that, the microgrid's maximum size could be verified. On the other hand, the stability study was carried out by performing input and output of loads when the microgrid is operating in island mode. After determining the size of the microgrid, tests with input and outputs of nominal loads were performed again. The objective of this test was to verify if the generator was able to maintain the stability of the system after the disturbance. And finally, the short circuit studies were carried out to determine the settings in the protection relays of the protection relay of the PSP and the MCB relay, the relay from the generation. Uh, these studies was focused on the island mode operation, since the parallel operation to the grid was it was the same that before the microgrid project started. When the microgrid is operating in parallel, oh, sorry, um, let me see. Through these studies, the cases we run was the a lot of kind of faults along the grid, and we also make the simulation of lack of power outage to the microgrid area too. At the end of these studies, we would like to see the if the algorithm of the microgrid was working as we planned, and we can see these things using the the RTDS operating with the CHIL mode. I think I answered all the points.
Yes, thank you very much. Okay, we're getting close to 10 here, so let's have one more question for Mustafa. Mustafa, can you expand on the RTDS hardware configuration in terms of processing? So the network you were simulating, was it spread over multiple chassis? Did you encounter any issues with node limits on the Nova Core? Okay, we might be having more technical difficulties on Mustafa's end. Just give him one more minute here to see if he wants to come in with an answer to the question. In the meantime, I will say that a couple people have asked about whether the presentation will be available. Yes, it will. Actually, you can download it right now in the handouts section. There's some PDFs with the presentation slides. And then also, we'll be emailing you a link with a recording of this presentation. So the webinar will be available. If you have colleagues who want to view it on demand, they can do that as well. Okay, unfortunately, I don't think we're going to hear more from Mustafa. So with that, I think we'll close the webinar. Thank you so much to all of our presenters, and thank you very much to our audience as well for your participation today. And I hope to see you next month. Bye, everyone.